Good day, grade 12 learners. Welcome to today's mathematics lesson. My name is Annelen Sindane. This lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Our lesson for today is probability, and we are going to look at independent events. We are also going to look at contingency tables, as well as tree diagrams and Venn diagrams, those that involve more than two events. At the end of the lesson, you should be able to use Venn diagram as an aid to solve probability problems. We should also be able to use tree diagrams as well as contingency tables to solve probability problems. We should also be able to understand the concept of mutually exclusive events, complementary events, as well as exhaustive events. We touched this last time, but we will go over it again as these are important basic concepts. We should be able also to use the probability identity. We know it. And we should also be able to use and derive the probability identity formula for three events given a sample space. And we should also be able to identify dependent and independent events and use the product rule for independent events, which is given by probability of A and B is equal to the probability of A times the probability of B. We can refer to the CAPS document on those pages, as well as the grade 12 examination guidelines for 2021 on page 7. Now, we need knowledge on our Venn diagrams, mutually exclusive events. We talked about them. The definition of probability, we'll go over it again. Outcomes, exhaustive events, knowledge of solving equations, as well as the product rule. And I will start by looking at our probability scale. We said the definition of probability is the measure of chance or likelihood of an event occurring, and it is given by a number between 0 and 1, and that number is a decimal or a fraction, or we can express it as a percentage, where we are saying if we have a probability of 0, the chance is it's 0, meaning it's impossible for that event to occur. If the probability is 1, we are certain, and if the probability is 0.5, we have an even chance. Now, the probability of an event, we said it is the probability of an event is given by the number of times or outcomes for that particular event over the total number of all outcomes in our sample space. And we can use the notation on the right where we're saying P of an event is given by the number of times an event occurs over the number in our sample space. And we remember our probability identity, which is given by the probability of A or B can be given by the statement below. Just to use colors to just try and get a perspective of this identity. The probability of the shaded area, the one in red, as well as the other one which looks like pink, we are saying it is the probability of A, the shaded part, plus the probability of B. We subtract the intersection. Remember, there is that part to complete the other circle. And we are saying we are subtracting this intersection because it's a repeated one. If you look at the probability of A, this part is there. If you look at the probability of B, this part is also there. But this is the common area that we are subtracting because it is added twice in this particular case. Hence, we subtract it there. We shall move on and revise our mutually exclusive events, where we have A and B. The events are disjoint. There is no intersection when we look at mutually exclusive events. And we know that the probability of A and B will be given by 0 as there is no intersection. And for mutually exclusive events, using the identity, where we have AND, we have substituted with 0, and therefore we can use the probability of A or B is equal to the probability of A plus the probability of B when you are talking about mutually exclusive events. We move on to complementary events. We touched these last week, that's why I'm moving very fast on them. The probability for mutually exclusive events, we have looked at them. We said the probability of A or B is given by the probability of A plus the probability of B. Complementary events, these are events that are both mutually exclusive as well as exhaustive. And we know that the probability of A or B is equal to 1, and the probability of A and B is 0. And if we combine this to the probability identity, we are able to say the probability of A plus the probability of B must give us 1. And we know that if A and B are complementary, then the B becomes what is not in A. So meaning the probability of A plus the probability of not A must give us 1. And therefore we'll have the probability of not A as 1 minus the probability of A, or the probability of A given by 1 minus the probability of not A. And we know that using a Venn diagram, the shaded area there, it's the probability of not A, and A, it's what is left. I can shade it red, the inside there. Everything inside set A becomes the probability of A, and everything outside the shaded red area becomes the probability of not A. And we can also illustrate that they are exhaustive in that it takes up the whole sample space. For example, if we have the outcomes from rolling a dice, we are able to see that our outcomes are 1 up to 6. And then if event A, it's getting an even number, it will be 2, 4, and 6. There are 3 of them. Getting an odd number, it's 1, 3, 5. You can see that it takes up the whole sample space, and we call these complementary events. They are also exhaustive. We move on to independent events. This is a new concept. So if we are talking about independent events, the occurrence of one event does not affect the occurrence of the other event. If you toss a coin twice, if the first outcome is a head, you cannot therefore guarantee that the next outcome will also be a head, because what you obtain in the first toss does not affect what you get in the next toss. Therefore, also at the same time, I can toss two coins at the same time and I can get different outcomes, because the occurrence of any one of those outcomes is not influenced by what the other event outcome is. We can also toss a coin and roll a dice at the same time. What I get from the coin does not affect what I will get from the dice. Therefore, we say the events are independent. There is no influence. Occurrence of the first outcome does not affect the next outcome. So if we have two events that are independent, we will always say the probability of A and B will be given by the individual probabilities of the outcomes of event A as well as event B. As an example, if A and B are two independent events with the probability of A being 0.6 and the probability of B being 0.5, we need to determine the probability of A or B. Now, the first thing that comes into our mind is our probability identity. So it means we are going to have the probability of A or B is given by the probability of A plus the probability of B minus the probability of A and B. Now, remember what we said. For independent events, the probability of and, we know that the probability of A and B is given by the probability of A multiplied by the probability of the other event B. So we are able to make a substitution where we have A and we can substitute with this product on our equation down there, and we should be able to get our answer there. Let's do the substitution. We want the probability of A or B. So this will give us the probability of A is 0.6 plus the probability of B is 0.5 minus. So to get the probability of and, we will use the product rule, and this will give us 0.6 multiplied by 0.5, and in the end we are able to get the probability of A or B as 0.6 plus 0.5 minus, if we multiply this will give us 0.3, and effectively we'll get the probability of A or B as 0.8. In an exam, this question can come. If A and B are two independent events, given the probability that, determine the probability of A or B. They are, so we underline the word independent there. Sometimes the examiner will change and say, if A and B are mutually exclusive events, calculate the probability of A or B. We'll be knowing what to do next. So we'll move on to the next example. Events A and B are such that the probability of A, the probability of not B is 0.3, and the probability of A or B is 0.8. Are A and B independent events? Can I give you 1 minute to just try this one? 1 minute. Try to figure it out. I know it's a new thing, but let's try and do it. Basho kanjalo nje. Welcome back. I hope you have managed to figure out the solution. Now, events A and B are such that the probability of A is 0.5. Here, we are given the probability of not B. Remember, the probability of not B plus the probability of B. These become complementary events. They should give us 1. So in this case, we can't use the probability of not B. So we must first of all get the probability of B so that we are able to use our probability identity. I will do it this side. So to get the probability of B, it will be equal to 1 minus the probability of not B. That's what we must do first, which will give us the probability of B will be given by 1 minus 0.3, giving the probability of B as 0.7. Now, we want to check if the events are independent. So, to check if the events are independent, the first step, we know that if they are independent, the probability of A and B must be equal to the probability of A multiplied by the probability of B using the product rule. So we want to check. Let's go to our identity. So we are given the probability of A or B should be equal to the probability of A plus the probability of B minus the probability of A and B. Now, once we are here, we can make the probability of A and B the subject. We substitute, we get 0.5 plus 0.7 minus we want to find the product there. The probability of not B is 0.7, so that will give us 0.5 times 0.7, and this is going to give us our answer as 0.5. Sorry, I changed the subject, so here we must have the probability of O when we change the subject, because and is on the other side, so the probability of O is 0.8. Let's substitute correctly there, and where there is and, we now have O, so it has to go to the other side. So it's 0.5 plus 0.7 minus 0.8, because the probability of and it's on the other side now. And this will give us our answer as 0.4 using the identity or the probability equation. We are getting the probability of A and B as 0.4. Now, let's use the product rule to check if we are going to get the same answer. So the probability of A and B, I've written the formula up there, so I'll do the substitution. The probability of A, we got 0.5 multiplied by 0.7, and this will give us 0.35. So the question is, are A and B independent? What will we say? The answer will be no, because the answer that we get when we are using the product rule, it's not the same as the answer that we are getting when we are using the probability identity. So they are not independent, because we are getting, the other one gives us an answer of probability of A and B as 0.4, and when we do the product we get 0.35. So in essence, 0.4 is not equal to 0.35. Hence we are saying they are not independent events. Easy one. Let's move on. This is just a summary to help us understand the distinction between mutually exclusive events and independent events. So we are saying if you have two independent events, they cannot be mutually exclusive. They cannot. So Independent events will always have an intersection, remember, whereas for mutually exclusive events, they do not have an intersection, they are disjoint. So there is no end for mutually exclusive events. So I can summarize the differences in the table below. The probability of A and B for mutually exclusive events, we know that this is equal to 0. For independent events, the probability of A and B, it's given by the product, which is what we wrote. PA and B is equal to PA times PB. You remember that one. And we know that using the identity, the probability of A or B is given by PA plus PB. Remember, because we are saying here we have a minus 0. That is why our equation just ends there. Whereas for independent events, this must be equal to the probability of A or B should be equal to the probability of A plus the probability of B minus the probability or the product of the probabilities of A and B. Now, I want us to look at another way of representing our probability outcomes. We have looked at a Venn diagram, and just now we were discussing independent events. You will see that there is another way of representing our probability outcomes, which we call a table. I have an example that we toss a coin twice, and after each trial, we record which side lands up. What is the probability that the coin will land on tails twice? So there is our coin with the head and tails. We want to check the number, the probability that the coin will land on tails twice. Now let's check. So our possible outcomes, we have head and tails, and we have our sample space as head and tail. The number in our sample space is 2. So I can create a table like that. First toss, I can either get a head or a tail. So the second toss, I've written it underneath. So it means on the first toss, I get a head. On the second toss, I get a head. I write both of them on the same first toss, second toss. There is the intersection of my outcomes. First coin, I get tails, I get a head. First toss, I get a head, then a tail, they will intersect there. And then I can either get tails and tails like that. Now, from there, I am able to count the number of outcomes from my table. I can have a head and a head, a head and a tail and a head, and tail and tail. So I'm able to get the number in my sample space. I've indicated there it's 4 because I've got 1, 2, 3, 4 outcomes. The number where I have tail and tails, it will be 1. And therefore, I can use my probability equation. The probability of getting tails and tails will be given by the number of times I get tails and tails, which is 1, over my sample space, which is 4. So I'm able to determine my outcomes using a table. And I would have solved my problem for the outcomes. This can work even if you are using a coin and a dice. You can record, you choose which one you put up, because there is no independent or dependent variable here. You just come up with a table the way which will make your life easy so that you are able to identify your outcomes and we are able to get what we can get moving forward. I hope it's clear. Let me move to the next way. Yes. Now I want us to look at tree diagrams as a way of representing probability outcomes. I know we know a normal tree with roots underground that we can't see. There is a stem, there are branches, there are leaves, there are fruits on a tree. But what we are going to be interested in for our probability outcomes, we can use tree diagrams to help us represent probability outcomes. And in a tree diagram, the number of branches is going to represent our outcomes. Remember, when I was using a table, you saw that my rows and columns were representing the outcome that I can get. So using the table before, I had 2 columns as well as 2 rows because I had head and tails. I can still have head and tails like that. So each row and each column represent the number of outcomes. In a tree, the branches represent our outcomes and the stem will represent the process that we are going to be doing. For example, if we are tossing a coin, our stem becomes tossing and our branches will be the outcomes head and tail. If we are rolling a dice, the stem will be rolling a dice and the branches will be the 6 outcomes that are possible when we roll a dice. So this is an experiment. We are tossing a coin twice and we record after each trial whether the side up is head or tails. We want to find out the probability that the coin will land on tails twice. So let's look at our coin. It has 2 sides, head and tails. Remember, our branches will represent our outcomes. So I will have my tree diagram. It starts with the stem, we say the toss. But now remember, we cannot have more than 4 branches emanating from one, because we said a coin is tossed twice. So we can get the outcomes for the first toss, which are head and tails. That's our first toss. So from each branch, from each stem, we should have 2 outcomes. We can't have more than 4 because that's the mistake that we have, because normally we want to get to the answer faster than the process allows. So that's the first toss. If my first outcome is a head, I will make a second toss. I will record second toss. I can still get a head or I can still get tails after I got my first outcome as a head. Please check. I'm moving one branch at a time and I deal with it. I finish, then I move to the other one. If my first outcome was tails, I can still get the second outcome as a head or I can get it as tails when I do the second toss. Now, I'm able to represent my outcomes. For my outcomes, I have to follow each branch with its outcomes. So the first outcome, if we follow this branch that way, we are able to see that our outcomes, the first one was a head followed by a head. Second branch, the first toss, we got a head. And for the second toss, we got tails. So it will be head and tails. For the other one, the first outcome, we got tails, and the second one, we got a head. First outcome, tails. Second outcome, it's also tails. Now, so it means we are getting two heads, a head and a head, head and a tail. But now, the challenge is sometimes we want to also represent the probabilities on our branches so that it's clear how we are going to get our probabilities. Now, remember, the probability of getting head, it's 1/2. The probability of getting tails is also 1/2. So on our branches here, we can represent the probabilities. This is the probability of getting tails. This is the probability of getting head. If I toss again, this does not change. I'll have my probabilities on each branch as a half. And to represent my outcomes, remember we are saying the events are independent. So to get the probability of the first outcome, I'll multiply the probabilities on my branches. So meaning for the first outcome, I'll multiply the probability of half and multiply it by half. And that will give me half times half, and it will give me 1/4 as the probability outcome. For this one again, our first outcome, the probability is a half. They are independent. We get a half, and that gives us 1/4. Looking at the other branch, it's this half multiplied by that half. It will also give us half times half, giving us 1/4. And we look at the other one also, it's half times half, and that will give us 1/4. If you add the probabilities of this outcome, they must give us a sample space which is 1 all the time. And also check, when you look at the probabilities on your two branches, they should also always give you a 1. Otherwise, it will not be a correct tree diagram. So this is how we come up with a tree diagram to represent our outcomes. So what is the probability that the coin will land on tails twice? So in this one, it's straightforward. We go probability TT. So a tail followed by a tail. So these other ones will ignore them, and we have our probability outcome there as 1/4, which is the same probability that we got when we're using a table. We can move on and look at another one. Yes. So for our tree diagrams, it's not always about a coin. It's not always about rolling a dice. We can use this even for sweets. A teacher can have a bag of sweets. You pick a sweet from a bag without looking. Sweets can be red, blue, green. We can use those examples. Or we can use learners in class who are supposed to say in a speech. All those are examples where you can use a tree diagram to represent the outcomes. Now, let's look at this one. A bag contains 6 green balls, 4 blue balls. A ball is chosen. The color is recorded and the ball is placed back. A second ball is chosen and the color is recorded. What is the probability of choosing 2 balls of different colors? Blue and green. So to answer this one, this is an example. I will do it with you, and then I'll give you an activity after doing these 2 examples. So the first one, so we know we can write here a ball is chosen. So choosing a ball, it's what our experiment is all about. So we can have choosing a ball. So we can say this is the first, because you are picking first pick or first choice. You can get a blue ball, or let me start with green on top. Yeah, green and blue. Now remember, in this case, our sample space becomes the number of balls in the bag. So don't forget, so the number in our sample space is going to be 6 plus 4, giving us 10. So it means the probability of picking up a green ball becomes 6 over 10, and the probability of picking a blue ball becomes 4 over 10. For now, I would say do not worry about simplifying the fractions, because there is something that might change along the way. So we rather stick to the definition and not want to simplify too early. Now, if the first ball picked was green, there is a chance that the second ball can be green or the second ball can be blue. So that's a second pick. Also, if the first ball picked was blue, there is a chance that the second one can be green or the second one can also be blue. And we are able to represent our outcomes following our branches. It will be green and green. It will be green and blue. It will be blue and green. It can be blue and blue, like that. Now, but we haven't represented our probability outcomes per branch, so we need to go back. You are told that it's recorded and it is placed back. So it means you pick, you record color, you throw it back into the bag, meaning when I pick the second ball, I'm still picking up from the number of those 10. So my sample space won't change. So I still have my 6 green and my 4 blue, meaning the probability when I do the second pick, it will still, for green, I'll be picking from 6 out of 10. Remember, I'm picking 1. So the chance I can pick any one of the 6 out of the 10. And then I can also, for blue, we have 4 out of 10. I'm done with the top part. I go to the bottom one. The first ball picked was blue. The second one can be green. That's 6 over 10. The first ball picked was blue. The second one is also blue. It's still 6 out of 10. And that will give us the probability, as remember, these are independent events. First probability, it's 6 out of 10 multiplied by 6 out of 10. Second one, we have 6 out of 10 multiplied by 4 out of 10. Here we'll have the first one, it's 4 out of 10 multiplied by 6 out of 10 to get the probability outcome. Then we also have 4 out of 10 multiplied by, here it must be 4. 4 out of 10 multiplied by 4 out of 10. We can simplify this using a calculator. That will give us 36 over 100, and 36 over 100, 4 is a factor, that will give us 9 over 25. That one we are having 4 and 6, that's 3 over 5, that's 2 over 5. When we multiply that, what do we get? 3 times 2 will give us 6. Let me quickly use my calculator. 6 over 10 times 4 over 10, and that gives us 6 over 25. That one is just the change, so it will also give us 6 over 25, and this one will give us 16 over 100, which will give us 4 over 25. If you add these probabilities, you will realize that they will give us 1. 9 plus 6 plus 6 plus 4, that will give us 25 over 25. So our probability outcomes are correct. They are giving us the sample space. Now, from there, we go back to the question. The two balls chosen are of different color. Now, so we want to find P different color. Now, this will be equal to, it means it can be green and green, it can be blue and blue. So we can get the probability of green and blue, or it can be the probability, the first one will be blue, the second one will be green. We take those outcomes from the tree diagram. We have got green and blue, we got 6 over 25 plus 6 over 25, and that will give us a probability of 6 plus 6 over 25 will give us 12 over 25. You can simplify it. For P different color, we get our outcomes like that. So I hope it's clear. That's how our tree diagrams work. Now, the second one, we are saying example 2. This is what we have as a common. Can I give you 1 minute to just attempt this example now? The probability that it will be sunny tomorrow is 1 over 3. If it is sunny, the probability that Abuile plays soccer is 4 over 5. If it is not sunny, the probability that Abuile plays soccer is 2 over 5. Determine the probability that Abuile does not play soccer. I'll just give you 2 minutes to try and figure out a way of answering this. I know you have done this before. Let's quickly try it. 2 minutes. Let's try it. Welcome back. I know this one can give people a headache because they don't know where to start. Now, here we are looking at two things. We are looking at the conditions of being sunny, and we are also looking at the event playing. Now, when we are drawing a tree diagram for this one, you start by your branches. So there are two things. It can either be sunny or not sunny. We are given one probability there. The chances that it will be sunny, it means it's 1/3. So the chances that it will not be sunny becomes 2/3. Remember, I said to you always, when you are looking at your branches, there must be, and the probabilities must always add up to 1. Whether you are using numbers or you are using probabilities, they must give you 1 when you add the 2 branches or the 3 branches. Now, from there on, here we are looking at the weather conditions. It can either be sunny or not sunny. So remember, if it's sunny, he can either play or not play. Even if it's not sunny, he can either play or not play. So NP, it's for not playing. NS, it's for not sunny, the opposite of sunny. Remember, these are complementary events. They should always give us 1. So now, so it says if it is sunny, the probability that he plays soccer, sunny, he plays, becomes 4/5. So the probability that he does not play becomes 1/5. If it is not sunny, the probability that he plays becomes 2/5. Meaning, if it is not sunny, the probability of not playing becomes 3/5. Our outcomes, we have sunny and play, sunny, not play. Then we will have not sunny and play, and we will have not sunny, not play. We are able to calculate our probabilities. So this becomes, our outcomes becomes 1/3 multiplied by 4/5. That should give us 4/15. 1/3 times 1/5. That will give us 1/15. And then 2/3 times 2/5. That should give us 4/15. And then we'll have 2/3 multiplied by 3/5. That should give us 2/5. The question says, determine the probability that Abuyile does not play. If you look at this one, you are having the probability of being sunny and not play, which is that one. Not sunny and does not play, which is that one. So it's either it is sunny or it's not sunny, he does not play on occasions. So we can quickly say the probability not play will be given by the probability that we are having sunny, not play, plus the probability of not sunny and not play, and that should give us 1/15 for sunny and not playing. We are adding this to 2/5, and if we check the outcomes there, you are able to see that 1 over 15 plus 2 over 5 equivalent fractions. This will be 6 over 15. And we know that 6 over 15 plus 1 over 15 will give us 7 over 15. And that becomes our final answer. We get our 4 marks. Coming up with your tree diagram, determining the outcomes, we'll get our 2 marks. And then knowing that we are supposed to add the probabilities, we get a mark. And the final answer, that's where the 4th mark goes. I want to take you back a little bit. I want us to go back a bit. Right. Let's go there to tree diagrams. I didn't take you back enough. Now, let's look at the question where we have no replacements. You choose 2 balls, one after the other, but you are not putting back. I'll quickly do the tree diagram. Remember, we said first pick. Our sample space, 6 green, 4 blue. Our sample space is 10. So 6 over 10, 4 over 10. That is our green, that's our blue. When we do the second pick, I can still pick green or blue. If my first one was blue, I can still pick green or I can still pick blue. Now, if my first choice was green, it means now I'm not putting back the one that I pick. Meaning, for green, I'm now left with 5. If I've taken out 1, it means my sample space must become 9 as well. It goes down by 1 because it's no longer in the bag. If I check the other probability for blue, following my branches, this is the first time I am picking up blue. So I'm picking from 4, but my sample space is now 9. I will now move to the other branch. Our first pick was blue. And let's say our second pick is also blue. So I'm picking from 3 out of 9. 1, blue is no longer in the bag because I'm not replacing it. So it becomes 3 over 9. Then we move on. The first one was blue. Green, I'm picking for the first time. I'm still having 6 out of 9. Are you able to see how the probabilities work now? If you add 5 and 4, that gives you 9 over 9. That's a 1. 6 and 3, it gives you 9 over 9. Hence, our tree diagram will be fine. Then our outcomes, remember, it's green and green. It's green and blue. It's blue and green. And this becomes blue and blue. So once we are there, our probability outcomes becomes 6 over 10 multiplied by 5 over 9. And that should give us 1 over 3 by simplifying. That gives us 2 over 10. It's 3 over 10 multiplied, 3 over 5 multiplied by that one. We get 3 over 9, which gives us 1 over 3. 6 over 10 and 4 over 9 will give us 4 over 15. 4 over 10 and 6 over 9 will also give us 4 over 15. And 4 over 10 and 3 over 9 will give us 2 over 15. So we want to find the probabilities of choosing 2 balls of the same color. So here we want P, same color. And for the same color, we know that it can be the probability that we get green and green, or it can be blue and blue. And that should give us 1 over 3 plus 2 over 15. And That should give us 5/15 plus 2/15. It should give us 7/15. You are using your calculators, it's allowed. You are able to get your solution like that. So please, that's how the tree diagrams work. Let's move on now to the next part quickly. We have done this one, tree diagrams, we are done. Now, contingency tables. Contingency tables, we use them to determine our totals and missing values. Remember, if you add terms per row, they must give us the total. By column, they must give us the total at the bottom. So the question says we have 100 men and 200 women who are tested for color blindness. The results are written as follows. We need to find the values of A to E. So to get the values of A, we have the number of females and we have a total of 10 who are colorblind. So to get the number of males who are colorblind, we'll just say 10 minus 1. That will give our A as 9. To get our B, we know that if I add A and B, I must get 100, meaning B becomes 100 minus the value of A, which is 9. My B will be 91. To get my C, it is 200 minus 1, and that should give me 199. That's my C. To get my D, it becomes 91 plus 199, and this will give us our D as 290. And if I add 10 and 290, I'm getting my E, which is 300. And if I add the row, I'll also get 100 plus 200. I'm getting 300. I'm adding the columns. 10 plus 290, I get 300. So for each one, it can be a mark. Calculate the probability that a person chosen at random from this sample of 300 people is female. Please be aware that we are not doing conditional probability. Therefore, our sample space is always our total, which is 300. So P, female, you are looking at the total for females. We have 200 over the number in our sample space, which is 300. When simplified, that gives us 2/3. P, colorblind. I'll use CB for colorblind. It will be equal to, how many are colorblind? We are having 10 out of a sample space of 300, giving us 1/30 as a probability. We want to find the probability that a person chosen at random is female and colorblind. So female and colorblind, you are looking at going down, female, colorblind. They intersect here at 1. So the probability that a person is female and colorblind becomes 1/300. You have answered your question. We move on to the next part. Is colorblindness independent of gender? We have to motivate our answer. We have found out that this is 300, this is 290, this is 199, and this is 9, this was 91, like that. Is colorblindness independent of gender? We need to motivate our answer. We have done parts of the solution. We calculated the probability of being female. we said it's 2/3. The probability of being colorblind, we calculated and found it as 10/300, which was the same as saying 1/30. The probability of being female and colorblind, I'm choosing now. We want to find out, is it independent of gender? So that is why I'm using, because I've already answered this, so it's easier for me to use this. I want to check if the probability of being female and colorblind, this would give me female and colorblind. I got 1/300. Now, I want to check. Remember, if these are independent, it means the probability of being female multiplied by the probability of being colorblind, this should give us what? And should be the same as what I have there. So the probability of being female, I got 2/3 multiplied by the probability of colorblind irregardless of gender. We said 10/300, that gave us 1/30. Now let's do the calculation. 2/3 times 1/30, this will give us 1/2, there it's 1, 15, so it will give us 1/45. That's the probability of being female multiplied by the probability of being colorblind. So it's 1/45. The probability of being female and colorblind, it's 1/300. So we are able to see that 1/300 is not equal to 1/45. So therefore, we say they are not independent. Why? As our reason, the probability of being female and colorblind is not equal to the product of being female multiplied by colorblind. So therefore, the events are not independent. So if they are not independent, we say they are dependent. So it means colorblindness is dependent on gender. So these are the kind of questions you will meet in an exam, and we must practice them. Let's move on. Time is not on our side. Venn diagrams, we talked about the shape. We use rectangles and circles. Rectangles are for events and sample space, and our circles are for the events. We have talked about our event A in the sample space, A and B being disjoint. We said they are mutually exclusive there. We have talked about not A, the shaded area. A and B, the intersection, it's what is shaded when you are dealing with two circles, two events. A and B, A or B, sorry, you have all the events in the circles shaded. That's A or B. And then only A, you are seeing that the part excluding the of A excluding the intersection is the one that is shaded. A not B, you are able to see A or not B. So not B is everything outside B, including the intersection, because the intersection also includes A. Only B is the part that is shaded there. We are able to see that. Not A or B, you are able to see. Not A, it's outside, and the or B, you include the shading of B, excluding the intersection there. You are able to see that. Not A or B, you are shading outside the events that are intersecting. And we also see that not A or B, which is the same as saying not A and B, you are shading everything excluding the intersection. We have talked about the two events and the three events. When you have A1, A2 intersecting, we have that as a common area. And then we also have A or A1 or A2 or A3. You are able to see that. A1 only, you are able to see that it's only the A1 part that is shaded. So Venn diagrams, we can use numbers, or we can use our outcomes, or we can use probabilities in Venn diagrams. And when using Venn diagrams, we always start from the intersection and we work our way out. Let's check. We have a survey. So when the question comes in the exam, it can either be the Venn diagram with information, or you can be asked to draw a Venn diagram. So if we look at this one, the information on the Venn diagram is already given. So we are told how many customers did not buy our burgers on the day. You are able to see that there's only one value outside the Venn diagram. So it is easy for us to say 5 customers did not buy any of the burgers, because remember we said everything inside our sample space is drawn within the rectangle, and anything outside the events A that we are having here should be within the sample space. So they are 5 because they are not buying any of the given burgers. And now let me move to the questions. Our Venn diagram is that side. How many customers did not buy burgers on the day? I've said number, not buy, is equal to 5. You are done. You get your mark. There are 5. You are picking it from the Venn diagram. Next one, are the events B and C mutually exclusive? Give a reason for your answer. So we are looking at events B and C. Are they mutually exclusive? Remember, if events are mutually exclusive, they should be disjoint, but in this case, there is an intersection there. So we are saying no. Why? Because the number, you can use number in B and C, is not equal to 0. You have 29, 17 plus 12 gives you 29 there on the intersection. Therefore, we are saying the events are not mutually exclusive. Or alternatively, you can say there is an intersection as a reason. So no, because the number in B and C is not equal to 0. Remember, for mutually exclusive, the number in B and C, or the probability in B and C, must be 0. We move on now. If a customer from this group is selected at random, determine the probability that he or she bought only a vegetarian burger. Remember the shading that I showed you? Only the vegetarian burger. You are able to see that you are only looking at where I am shading here. And the number that we have there, it's 58 out of our sample space. Bought a cheeseburger and a bacon burger. You are able to see there the solution. We want to find cheeseburger and a bacon burger. We have seen that. We said we are looking at the intersection. So it's 17 plus 12 all this over our sample space. So we said P, V only. We said it's 58 over 240. You can simplify that. P, cheese, C and B. This will be equal to, we said this is 17 plus 12 giving us 29 over 240. You want to find the number that did not buy a cheeseburger. So a cheeseburger is everything outside C. So I can shade everywhere, excluding the C. So these ones inside C, we are not touching. We want those outside. So I can take 52 plus 3 plus 58 plus 5. It will give me the number that did not buy my cheeseburger. So P not C, we are seeing that will give us 118 over 240. You can simplify that later on and you are able to see the solution on the other side. Now, both a bacon burger or a vegetarian burger, you are able to see that it's an or, bacon burger or vegetarian burger. So we can use the numbers that we are having where we are saying it is the probability of V plus the probability of B minus the probability of B and V, and you're able to see that. Or you can use everything inside B and V. You are adding everything and you are not repeating anything there. And you will be able to see that it will be 58 plus 17 plus 12 plus 9 plus 3 plus 52. When you add those, they will give you 151 over 240, and that becomes your answer. Or you can use the identity. You can't include this. They did not buy anything. You can't include those 18. They only bought the cheeseburger, but we want the ones that had a bacon or a vegetarian burger. Our approach to questions: remember, you read and understand the scenario. You represent the given information. Is it a probability? Is it a number? We know that. You interpret the question, extracting key information from words like random experiment, mutually exclusive. You remember this. Represent our outcomes with appropriate diagrams, which will help visualization easier. We have discussed all this. And then you answer the question using the appropriate information accordingly. And I will ask you to answer this one. I'll give you 2 minutes to answer that question. 2 minutes. Let's quickly answer that. Right, welcome back. I hope this was not difficult. You want to determine whether the events A and B are independent or not. Show all relevant calculations. Now, remember, to show independence, we said the probability of A and B must be equal to the probability of A multiplied by the probability of B. Let's check. So this will give us 0.12 multiplied by 0.35. We get our solution. 0.12 times 0.35, and this will give us 0.042. Now we want to check we are given information. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. Let's check. On the left hand side, we are given that the probability of A or B is equal to 0.12 plus 0.35 minus, we have calculated that one, we got 0.042. We want to check. So we are going to have this becomes 0.12 and that one will give us 0.47. So we're having 0.47 minus 0.042, and that gave us 0.428. That's the probability of A or B. So using this, what we are given is equal to what we get when we are using the principle of independence. We can use that, or alternatively, we can just substitute and show that the product will give us the same as what we will get when we are using the equation, and we get our 4 marks. We move on to the next one, activity 2. I will give you 5 minutes to try and answer that question number 2. 5 minutes. Welcome back. I hope you managed to do something in the short time that I gave you. I was supposed to give you about 11 minutes, but because I want us to discuss this question together, hence I gave you a shorter time. Whatever you have done, we will mark, and then you will be able to do it on your own later on. Now, the question, we are given 52 learners like rugby. So we start from the top. Our sample space is 80. 42 like volleyball. 3 learners did not like any sport. X learners like all 3 types. 15, we have that information. Now, let's check how we should represent this information. So I'll use the information on the right. Remember, we said you always start from the intersection and you move outwards. So we are able to see that there are 3 learners who are within the sample space but outside any of the rugby, volleyball, and our chess, sorry. So now you are able to see that on the intersection we have X learners. That's where you start. 15 learners like volleyball and chess but not rugby. 15 learners like volleyball and chess but not rugby. What will we put there? So it means these 15 are on the intersection of volleyball and chess, but we do not include rugby. So I'll put 15 here. They are not part of the X who are doing all 3 because they are not part of rugby. So we are only going to put 15 for this intersection there. 12 learners like rugby and chess, but not volleyball. Rugby and chess, but not volleyball. I'll put the 12 there. 14 learners like rugby and volleyball, but not chess. So I'll have 14 here. And then 5 learners like chess only. 5 learners like chess only. It means here I'm putting a 5. Chess only. And then 42 learners like volleyball. So if I add everything here, it must give me 42. So to get those that like volleyball only, it will be 42 minus 15 minus 14, and that will give us minus these X who are doing all 3. So it will give me 13 minus X. 52 learners like rugby, so it is 52 minus 14 minus X minus 12. It will give me the number that like rugby only, and that should be 52 minus 14 plus 12. That gives me 26 minus X. So that will give us 26 minus X. The question was 5 marks. So you will get your mark for the 3, your X, the 12, 15, and 14, 1 mark, and then the 26 minus X and the 13 minus X there. We get our 5 marks. We are done with the Venn diagram. Now, we move on to the next question. There is our Venn diagram, our sample space. We said our sample space is equal to 80. We are able to get that one. And then the next question, we are supposed to find the value of X in 9.2. And for us to get the value of X, we must add everything in our Venn diagram and equate it to the sample space. Then we are able to get our X. So to do that, we will have 9.2, we will have 26 minus X. We are not going to repeat anything. Plus 14 plus 12 plus X plus 5 plus 15 plus 13 minus x plus 3. This should be equal to 8. I hope I've added everything. And then from there on, we collect like terms. X, negative x plus x will give us 0, 26, 14, that's 40, 52, that will give us 72, plus 13, we'll get 88. Yes, so we are going to get our answer as this negative x and that one will cancel, so we'll have 88 minus x is equal to 80, and taking x that side, we'll get our x as 88 minus 80, and we get our x as 8. So okay, that's our 9.2. We are supposed to also find out how many learners like rugby only. So we will go back and check how many learners like rugby only. You are only looking at those learners who took rugby only. We got that as 26 minus x. Those who liked rugby only, 26 minus x. And this means it's 26 minus 8. And that should give us 18 learners for rugby only. So N R only will give us 18 learners using subtraction. Then our 9.4, calculate the probability that learners chosen and randomly will choose at least 2 different sports. That one, you are going to add those at the intersection. Remember, we said our x is 8, so it will be 12, 14 plus 15 plus those 8. It will give us 49 out of 80. That becomes our solution. Or you subtract those who only liked one sport and those who did not do any sport, then it will give us the same answer as what we are getting when we are using both. Now, you can take a picture of this one. You will do it later on. This will help us practice a tree diagram, a different kind of a tree diagram. Okay, so take a picture. I'll move on. I will move on. This is the same question. You don't have to. You can take a picture of this one as well. Let's take a picture of this one. We'll do it later on. That's our activity 4. I'll try to move faster. It takes me back if I try to move faster. I will wait for it to move well. You are able to take the pictures of the answers as well, of the solutions. The homework, take a picture. The solutions are there. It's another Venn diagram for the homework. Take a picture. We are able to see the questions there and the solutions. Now, the definition of probability is a measure of chance or likelihood of an event happening. Independent events, we saw that the occurrence of one event has no influence on the occurrence of the next event. And we know that for independent events, we use the product rule. And if the events are independent, the probability that you get on end must be the same as the product on the right hand side, exactly the same, not rounded off. They have to be exactly the same. And we mostly use this on our contingency tables mostly. For our mutually exclusive events, these are events that cannot occur at the same time. And we know that for mutually exclusive events, the probability of A and B is 0. There's no intersection. The product rule, the probability rule, we must know it and use it, especially when we are given probabilities and we have to find out the missing probabilities of A or B, probabilities of A and B, finding the probability of A given part of the information and the other one is missing. We are able to see that Venn diagrams and contingency tables are used as a way to represent probability outcomes and are also used as aids to help us solve probability problems, and we must use them as such. They help us visualize and make the problem much simpler. And we know that our probability is always a fraction or a decimal in the interval 0 to 1, and sometimes the probability can be given as a percentage. Thank you for attending and watching the lesson. Hoping to see you in future. Let's prepare for our prelim exams, and I wish you all the best. I thank you. Have a good day.